Okay, so let's go ahead and finish off the thermodynamics chapter. In this last little bit, we will cover basically just Hess's law. Okay, so for a chemical reaction to occur, it must have two things. Okay, so it has to have the right thermodynamics, and it has to have the right kinetics. And as you well know by now, in thermodynamics, what we talk about is energy. So it has to have the right energy. So for instance, if it's a reaction that needs energy to go forward, then we have to supply the energy. And that could be, for example, in the form of heating a reaction. But it also has to have the right kinetics. Okay, and by kinetics, what we mean is it has to have the right activation energy. Okay, so in other words, if we go back to our ball on the hill analogy, so that activation energy might be you pushing the ball off. Okay, and it has to have the right collisions. Okay, so for two molecules to react, they have to collide. They have to meet each other. Okay, so if we have those two things, that's basically the groundwork for a reaction to occur. But it also needs a driving force. Okay, so for reactions that are product favored, it has to have a driving force, such as the formation of a precipitate, in other words, the formation of a solid. It could be the formation of a gas, formation of a pure liquid like water, or it could be electron transfer, like a redox reaction. Okay, so it has to have some reason for occurring. So the first one, if I was to, for instance, just put two salts into water, for instance, and there's no precipitate from those salts. Okay, so maybe I put in sodium chloride and let's just say potassium chloride. And basically what I've done is I've just made salt water. If nothing precipitates out, then really has any reaction occurred? Okay, so kind of keep that in mind, that if nothing happens, if nothing changes, how can you really say a reaction's occurred? So it has to have one of these driving forces. So formation of a gas, so you may see it bubbling, for instance. Formation of a pure liquid like water, okay, or electron transfer. So one of those has to be taking place in order for us to say, yes, a reaction occurred. And it's also just so happens to be the driving force for a reaction, meaning that it's actually needed for the reaction to occur. So it sort of drives the reaction forward. So just to remind you, enthalpy, we talked about this before, but it's just basically the energy in a reaction. So the total kinetic and potential energy of a system at a constant pressure. Okay, and remember we can calculate the change in enthalpy as a state function. So just say the enthalpy of the products minus the enthalpy of the reactants. Okay, and these are always going to be in joules or kilojoules per mole. Okay, so as we've said, since we are talking about enthalpy as being a state function, okay, we realize that it's independent of pathway. Okay, so we can calculate delta H by just saying H final minus H initial. Okay, and down at the bottom we see that if H final is less than H initial, in other words, if the energy it ends up with is smaller than the energy it started with, so we're talking about the system, then this is an exothermic process. If it ends with more energy than it started from, then it's an endothermic process. So just like we said before. So if energy goes into the system, it's endothermic. If energy comes out of the system, it's exothermic. And depending on what reaction system you're talking about, either of these can be true. So it's not just that, oh no, a reaction has to be endothermic to be real. That's not the way it works. So some reactions are exothermic, some reactions are endothermic. Okay, so there's sort of a reminder there. So one way we can calculate enthalpy, so we've said, well, okay, we can calculate it by knowing where we end up with and where we started. Okay, but what does that mean really? Well, one way we can calculate enthalpy is based on standard conditions. So STP, standard pressure and temperature. So pressure 1 atm, 1 mole is our concentration, and our temperature is 25 C, in other words, room temperature. And what we have is what we call standard enthalpy values. So we add this little naught symbol. So this would be pronounced delta H naught, you could say. Okay, so and these are listed in tables. Okay, so under standard conditions, we know how much energy is evolved or gained for any given reaction, or most reactions. Okay, and we know them at standard conditions, so we say delta H naught. Okay, so the delta H naught values, you can look these up in a table. Okay, and these are in kilojoules per mole. And just remember, so they make a note here that anything in the standard states, in other words for elements, will always be 0. Okay, so the delta H naught for any elemental atom is just 0. So things like carbon, or so just solid carbon, will be 0. Bromine, so Br2, okay, that will be 0. And then something like O2. So if it's the way you would find it on the periodic table, then that's going to be 0, delta H naught. So just keep that in mind moving forward. And we can use these when we calculate, or we can use Hess's law to use these to calculate delta H for a reaction. Okay, so what Hess's law states is that if a reaction can take place by one or more route, and the initial and final conditions are the same, the total enthalpy change is the same. Okay, so what we mean is, so it's kind of stated a little bit better at the bottom. So the heat of any reaction, delta H naught F, or delta HF naught, however you want to say it, for the specific reaction is equal to the sum of the heats of the reaction for any set of reactions in which the sum are equivalent to the overall reaction. So I think that's probably a better way of stating it. Okay, but what that means is, so if I can, for instance, find the standard enthalpy for a reaction that can make up the reaction I'm looking for. So for instance, if I want to have this reaction, so I have reactants on the left, products on the right. So I have carbon reacting with water to give me CO2 and hydrogen. Okay, so if I want to know, so I have a question mark here. So I want to know what is the enthalpy change for this reaction. Okay, but maybe this is not a known reaction, so it could be that you could look this up in a table and oh, it's already there. Okay, or it could be that I need to look up things like, okay, the formation of water and the formation of CO2 and hydrogen. Okay, so starting from the elements that make them up, so for instance, starting from carbon, hydrogen, and oxygen, if I know the enthalpy of the reactants and I know the enthalpy of the products, well then the difference between those two must be the enthalpy for this middle arrow. Okay. So if I know the enthalpy of my products and I know the enthalpy of my reactants, then the difference between this value and this value will give us our enthalpy for that reaction. Okay, so hopefully that makes sense. Okay, and that's when our delta H of reaction comes into play. Okay, so we're going to use the sigma notation for this, and all that means is that you would just total up all the enthalpies for everything on the left and everything on the right. Okay, so you would total up all the enthalpy. So if you have multiple reactants, multiple products, you would total their enthalpies and then use that new total as the total for the products and for the reactants. Okay, and this is a topic we kind of briefly cover now, and then, like I say, in Chem 2, you'll really dig further into this. So let's do an example here. Okay, so looking at our same reaction. Okay, so they give us the two enthalpies. So they tell us the enthalpy for the reactants is minus 43.6 kilojoules, and they tell us the enthalpy for the products is minus 393.5 kilojoules. Okay, so if I want to calculate the total enthalpy for the reaction where I have carbon reacting with water to give me CO2 and hydrogen, then what I want to do is I want to use these values and my delta H equation. Okay, so all I want to do, remember, it will always be products minus reactants. Products minus reactants. Don't do it the other way around, because if we do it the other way around, our signs will be wrong, and your ultimate, what you calculate, will be wrong. Okay, so I want to do products. So my products was minus 393.5, so here's my products, minus my reactants, which is negative 43.6. Okay, so notice we keep our negative sign. Don't let it go away. Okay, and then we just find the difference between the two. In other words, we will add 43.6 to minus 393.5. Okay, so the total is 90.1, a positive 90.1. So this tells us that this reaction is endothermic. Okay, so I have a positive change in delta H. Okay, so this will be an endothermic reaction. And that's really all there is to it for Hess's law. It gets a little more complicated when you have more complex reactions. And there's one other way I'll teach you how to calculate with Hess's law. Okay, but that's really all there is to it. So if I want to know the enthalpy change for a reaction, if I can find reactions that make up those elements, okay, then take the difference of those, okay, well then I can determine the enthalpy change for a reaction. So there's two methods to do this. So we have the direct method, which is what I just showed you. Okay, so if I use a table of values and I look up and I get delta H values, okay, this is the direct method. Okay, if I cannot do this, I can use what's called the indirect method. Okay, so if I can't find, so maybe I'm doing a new reaction in the lab and it hasn't determined what the delta H is yet. Okay, so what I can do is I can set up a series of reactions and find the difference in those, and that will ultimately tell me the missing value. Okay, so I'll show you what I mean. Okay, so this says, using Hess's law, the direct method, calculate delta H for the following reaction. So we have water reacting with a graphite to give us H2 and CO. Okay, so the first thing we want to do with this is to make sure it's balanced. And by the way, this is the direct method again. So we'll look at this example and then we'll look at the indirect method later. Okay, so first thing, make sure it's balanced. Remember now I said now that you know how to balance reactions, make sure that you always check to make sure a reaction is balanced. Okay. Now, you'll go to the thermodynamic tables and you want to look up the values. Okay, so in this particular instance, the only two values we have to look up, make sure you always look at your states, because if this was liquid water, it would be 0. So carbon in solid form will be 0. And here I have H2, just as it appears on the periodic table. So this will also be 0. Okay, so the only two things I need to look up are carbon monoxide and H2O. Okay, so I just go to the tables and make sure you look at your states, because these will change depending on the state. So for instance, if this was carbon monoxide solid, it's going to have a different value. Okay, so just go to the tables, find your values. Okay, now use Hess's law. So just take the difference between those two. Okay, so this is what the sigma means. So on our product side, I have H2, which is 0. So this comes, I'll just write this out. So this comes from H2. And then I actually have a value for CO, so this part comes from CO. And notice I say times 1 mole, because I just have 1 mole of it. If I had 2 moles of it, I would say times 2. Okay, then on my reactant side, okay, I had to look up the value for water, so this comes from H2O. Okay, but remember, we said that for carbon, since it's in elemental form, and it's a solid, okay, it will just be 0. Okay, so then I just take the difference between those, and I'm just moving this so I can put the answer up. Okay, so now I just take the difference between those two. So you would first total up the products and total up the reactants, and then take the difference of those values. Okay, so here we have a positive 131 kilojoules, and delta H is positive, so we know this is an endothermic reaction. And they won't always be endothermic, okay, but this one happens to be. Okay. Let me unpin this so you don't have to see that anymore. Okay, so now it wants us to calculate the heat of combustion of methanol. Okay, so we have a reaction, and then we have some values. Okay, so using the direct method, try to calculate the delta H for this. Okay, so hopefully you were able to get this one. Let's go over it real quick. Okay, so remember, we're using the direct method, so we want to use our delta H equation. Looks like they've balanced this already for us, but make sure you double check that. Okay, and one handy thing is to write out the equation like this. So without actually putting values to it, you can just write out the equation. So I know on my product side, I have the delta H, there we go. So I have the delta H of CO2, okay, and I just have one of them, so no need to write times 1, plus 2 times, and that 2 comes from here, 2 times the delta H of water, and it's gaseous water, minus 3 halves, okay, delta H for oxygen, so I just bring my 3 halves down, so that comes here, okay, plus the delta H of methanol. Okay, and if we go back to our values, you'll notice one value they didn't give us, oxygen. Why? Because remember, this is in elemental form, so it will be 0. Okay, so now all I have to do is literally take the numbers they gave me, plug them in. So here I have minus 393.5 times 1, again, because I just have a 1 in front of CO2. Okay, and then plus 2 times my delta H for H2O, gaseous H2O. Okay, and remember there's 2 of them. Plus, or minus, excuse me, 0, because oxygen is 0. Plus 1 mole times minus 201.5 kilojoules per mole. That's just my enthalpy for methanol. Okay, and now you want to total each side before you subtract them. Okay, so total each side. So on my left-hand side, I have minus 393.5 kilojoules per mole plus minus 483.6 kilojoules per mole minus a negative 201.5 kilojoules per mole. Okay, and then just take your difference. And it turns out for this reaction, we have minus 474.1 kilojoules per mole. Okay, so this is an exothermic. Okay, so since I have a negative delta H, this means it's exothermic. So the surrounding temperature increased. Okay, sorry, I had to pause for a phone call. Okay, and so what we said is the surrounding temperature increased, but the overall energy of the system decreased. So always remember, if one energy is going up, that means the energy of the other has to be going down. Energy has to go somewhere. Remember, what law was that? It was what? The first law, right? Okay, so make sure you don't forget that. Okay, so now what if, for instance, we know the enthalpy for 2 reactions, but we don't know it for a third reaction. So this is our same reaction. So we have, this is a different one, excuse me. Okay, here we have carbon reacting with oxygen to give us carbon monoxide. Okay, so we don't know directly the enthalpy change for this reaction. But what if I can set up 2 equations that if I add them together, they give me this equation? Okay, so what if I say carbon plus oxygen gives me CO2? Okay, because I know this value, but CO2 isn't quite what I want. Okay, I want carbon monoxide. Okay, so it's almost the right reaction. But then I have a second reaction that's also known. So carbon monoxide plus 1/2 oxygen gives me CO2. Okay, so what I have to do now is I have to rearrange these equations, and you'll learn later on that there's multiple ways I can multiply them, all kinds of things like that. But for now, as tough as it will get is that I want you to be able to rearrange equations to get this top equation, to get the goal equation. So what we have to do now is we have to figure out, how can I rearrange those equations? So how can I rearrange these equations in order to get this top equation? So if I think about this, so I want CO on the right-hand side. Okay, so right away I know I need to reverse this equation because it has CO on the reactant side. Okay, but I want carbon monoxide on the product side. So instead, if I write this reaction, so if instead I say CO2 gives me CO, gas, and this is gas, plus 1/2 oxygen. Okay, now I have carbon monoxide on my right-hand side. Okay, and then if I add together my original reaction, so let me give myself some more space here. So if I write this, C solid plus O2, sorry, this is supposed to be carbon, gives me CO2. Okay, then I add these together. And now anything that's on both hand sides, or both sides of the reaction arrow, I can cancel. So CO2 will cancel with CO2. And then this 1/2 oxygen will cancel and make this now 1/2 oxygen. Okay, so what I end up with then is carbon plus 1/2 O2 gives me CO. Okay, and that's exactly what I wanted. Now, what do I do with my values? So my value for the top reaction, so this C plus O2 gives me CO2, that didn't change. Okay, so I didn't do anything with this value, so I'll write minus 394 kilojoules. But what I reversed the second reaction, so equation 2. So what you do when you reverse a reaction is you change the sign. So this then becomes 283 kilojoules. Okay, and then I just need to total these. Okay, so I have 283 plus minus 394, which gives me minus 111 kilojoules. Okay, so I'm just adding these together. Okay, that's all there is to it. So I won't make them any tougher than just having maybe to flip a reaction or two. But there's lots and lots more rules that you'll learn later on in Chem 2. Okay, so let's double check that we were right. So I've written all this out for you. Okay, so if a reaction is reversed, change the sign of delta H. Okay, and then if equations 1 and 2 are multiplied or divided to obtain correct quantities, then delta H is also multiplied or divided. So make sure you know that these two rules. So if we reverse it, change the sign. If you have to multiply or divide by a number, the delta H also gets multiplied and divided by that number. Okay, so just make sure you know those rules. Okay, so here, yeah, our answer was right. So we flip the second equation, add them together, and it gives us the right equation. And we flip the sign of this guy since we reversed the reaction. Okay, so that will wrap it up for Hess's law. That will wrap up our thermo chapter.